In this video, we're going to talk about Lechatellier's principle as it applies to equilibrium systems. And what it basically states is that whenever you apply a stress to an equilibrium system, meaning you kick it out of whack, the system's going to work its way back to establishing those K values and the ratio of product to reactant that it would be defined as K. So first, let's take a look at a couple factors that actually affect the ratio of products to reactants at equilibrium. So it's changing the K value. And the two things that can do that, one is temperature, and that's for all systems, but then pressure for gases. So first, let's take a look at an example where the temperature impacts the ratio of products to reactants. And the demo that we'll look at is the cobalt chloride, which forms a different complex when it's with cold water than when it's with warm water. And they actually interact with light differently, hence you see the different colors. You see purple cobalt chloride, and you see the blue cobalt chloride, and that's in the warm. So cold, purple, warm, blue, same material. So I basically wrote that up here as this expression right here. So cobalt chloride, when I added energy to it, and that's what happens when you put it in warm water. I'm adding energy to it. I'm basically adding a reactant. And what that does is it pushes the reaction forward to make more product. So we can see that in the warm system, our K value would be greater than 1. And then in the cool system, we have a K less than 1. So we can actually change that K value by changing the temperature. And this is true for any endothermic reaction, that you would have the K be a higher value at warmer temperatures and then a lower value at colder temperatures. If it was an exothermic reaction where energy is released, essentially you can think of energy as a product, not like in this case. And in that case, you'd have the opposite effect, whereas if you have a higher temperature system, it's going to push the K value to be less than 1. And then if it's you cool it off, it's going to go the other way and K value will go up. Now when we're looking at gases, what happens is when we apply a pressure, it's going to favor the system that has the fewest number of moles of gas. So if we look at the production of ammonia, you can see that the reaction is 1 mole of nitrogen react for every 3 moles of hydrogen to make 2 moles of ammonia. So essentially we know that a mole of any gas at the same temperature and pressure conditions is going to occupy the same volume. So let's just say at STP this is happening. Well, at STP, the 4 moles of gas, or the reactant side, is going to want to take up 89.6 liters, which is quite a bit more than the amount of space that 2 moles of gas would occupy under those same conditions. Therefore, we can say that when you increase the pressure, it's going to favor the fewer moles of gas because it's basically, you can think of it as it's trying to take up less space with fewer moles of gas. So it kind of works with the pressure. Now, factors that don't affect K but affect reaction rates would be if adding a catalyst. If you add a catalyst, it speeds up the reaction rate so it gets to equilibrium faster, but it doesn't change what that ratio of product to reactant at equilibrium actually is. You can also change reactant or product concentrations, and that'll kick a system out of equilibrium temporarily, but it's still going to work its way back, so it doesn't actually affect the K value. Now, we've already defined this in a previous video as Q, which is the concentration ratio of products to reactants at any point in time. If Q is equal to K, then you're at equilibrium. But if Q is less than K, that means you have a lower ratio of products to reactants than is desired. And if Q is greater than K, it's going to mean that you have a greater ratio of products to reactants than desired at equilibrium. So if you have a Q less than K, that favors the forward reaction. If you have Q greater than K, that favors the reverse reaction. So let's take a look at an equilibrium system that happens with butane. So butane will actually convert itself into isobutane. They're structural isomers of each other. They have the same chemical formula, but just a different arrangement. But both are C4H10. It's an equilibrium reaction, and the K value for this reaction is 2.5. So if at equilibrium we could have, this is just an example now, we could have concentrations of butane, which is the reactant, of 0.5, and isobutane of 1.25. So if I ask you, what would happen if I added more reactant? We should be able to just intuitively predict it. Well, if I add more reactant, I'm going to be forming more product. So we can quantify that with Q and see that that would happen. So what would happen if I increased the molar concentration of butane by 1.5 molar? Well, Q then, your amount of reactant is now 2.0 molar. The product is still 1.25. That gives us a value of 0.625, which is substantially less than our K value. So what's going to happen is more of the product is going to be made to kind of get back to that value of K. So in order to quantify this, we're going to use a Rice table. Rice standing for reaction, initial concentrations, the change in equilibrium concentrations. So we know that at this point we have a 2 molar concentration of reactant and a 1.25 molar concentration of product. We know that some of that reactant is going to get converted to product, and we can define that value as x. So that's going to go down by x, and that's going to go up by x. So at equilibrium, we would say we have concentrations of 2.0 minus x for the butane and 1.25 plus x for the product. And then we can set that equal to k. So k is going to be equal to 2.5, and that's going to be equal to 1.25 plus x over 2 minus x. When we rearrange and solve for x and combine like terms, we solve that x is 1.1. So what that means is the concentration of butane is going to go down by 1.1, and our concentration of isobutane is going to go up by 1.1. So that would give us a 0.9 final concentration there, and a 2.35 concentration here. And just to show that you got back to equilibrium, we see what Q is equal to at this point. And because we rounded to 1 sig fig here, it kind of messes it up a little bit. But you essentially get 2.5, showing that you're back at equilibrium. So there are things that can affect what our actual equilibrium constant is, and we have things that can perturb our equilibrium situation that our system will work its way back to in order to reestablish that equilibrium.